welcome to MLDon. So the last time we talked about the prior, likelihood, posterior, Bayes rule, and how we can introduce the idea of supervised learning into our math. So this is the second video of that series where we're going to continue with our discussion. But before we do, I'd like to do a little bit of recap as to what we talked about. So we talked about the Bayes rule. We talked about our, basically this is the notation that we're gonna work on for the rest of the series. So the posterior, the probability of this guy right here, this is the probability of how much we believe in our model to be true given a set of data, D. And then we said that according to Bayes' rule, it equals to the likelihood multiplied by the prior divided by the evidence. So the likelihood, we talked about it, so it means that if we assume that the model is indeed true, meaning that given the model is true, right? So that this guy right here, this vertical line is the condition, right? So given that our model M is true, how probable is it to observe D, or basically our observations? And the prior is basically how much we believe in our model to be true, regardless of what we observe, right? So if you notice, that is the big difference between the posterior and the prior, right? So prior means that how much do you believe in your model to be true, but posterior means after observing observation D, how much do you believe in your M, in your model? So as you may have realized, the more data you see, the more and more you realize how confident you are in your model. And last but not least, in the denominator here is the evidence. So the probability of observing D, regardless of your model. So remember, the evidence has nothing to do with M, with your model. And this is an important part in this series, so remember that. And then we said that for convenience purposes, it is customary to take the log of both sides. So we said that, okay, the probability of M given D, and then the right side that we just talked about, so we can take the log of both sides. The log of M given, and probability of M given D equals the log of the denominator. So the division, we said that it turns into a minus, and then the log of probability of the observation. And we said that we used this formula right here to do that. So the log of A over B equals the log of A minus the log of B. Right, and then over here we have a log of a multiplication, and we use this rule number 2 over here. That turns the multiplication into the sum of logs. So remember that this is also important. So if I tell you that what is the log of, say, multiplication of x of I starting from, say, 1 to capital N, right? So this means that what the log of x1 multiplied by x2 multiplied by x3 all the way to the probability of x of n, right? So we just said that if you have the log of some multiplications, you can distribute the log among each one of those variables and simply replace the multiplication by a sum. As you see here, A multiplied by B has turned into sum of logs, right? It's the same story here. Log of a multiplication equals a sum of logs, basically. So you can turn this into a sum, using a sigma, of, again, I goes from 1 to n, of log of x of I, right? Meaning that this equals log of x of I, sorry, x of 1 plus log of x of 2 plus all the way to the log of x of n, right? So by the same logic, the log of likelihood multiplied by the prior of the model has turned into a plus over here. So the sum of logs, log of likelihood and the log of your model, and then the rest is the same. So this is an important formula. We talked about that, and then we said that basically using the MAP or the maximum a posteriori estimation, if we say that the log of posterior equals the log of likelihood plus the log of the prior of the model minus the log of basically your evidence, we said that we can turn into we can interpret this whole thing as an error function, right? So we said that the error, or capital E, equals the minus log of posterior, and then we basically multiplied the whole thing by a minus, right? So if you compare this line with this line over here, all it has is just a minus as we multiply by that. So we always want to maximize the posterior, right? We want to maximize the confidence that we have into our model over here, given our observation, right? So maximizing that actually equals minimizing minus that, right? So the smaller this negative guy over here gets, it means the bigger this guy is getting, right? So why do we do that? It's because we are always well used to minimizing error. So whenever we talk about error, we want to make it as small as possible. But again, the contradiction was that we want to maximize the posterior, which is maximizing the log of posterior, both are the same thing. So in order to basically make it more intuitive, we multiplied everything by the minus to say that, okay, we want to minimize this because now we call this error, right? And we said that since we have the prior over here, as long as we have it there, we call this maximum a posteriori estimation, or MAPE, right? And then we said that MAPE can turn into MLE, which is the popular and famous maximum likelihood estimation, if we ignore basically the prior, this guy right here, right? And then why have we eliminated this guy over here, the probability of observation? It's because in the maximization process, the probability of observing the data has nothing to do with your model. Remember, in machine learning, you want to train the model, right? You want to come up with the best set of parameters. Learning means updating the parameters of your model. If you have a multi-layer perceptron neural network, learning means finding the best set of weights. You've got tens and tens of thousands of weights, finding the best values for each and every one of them, right? So that process of updating the weights over and over to find the optimal ones, that is the process of learning, right? So in order to optimize those weights or your model, you deal with the whole maximum a posterior estimation or the maximum likelihood estimation. So in order to maximize your likelihood, in order to maximize your a posteriori, which means basically maximizing your likelihood, here you do not basically consider the probability of observing D, because that has nothing to do with your model. What you see has nothing, as your data, has nothing to do what you have in your model as your parameters. So the probability of seeing that Has nothing to do the probability of how much you believe in your model, or the values that the parameters of your model have. So that is why during maximization we ignore this guy right here, right? And we deal with, I mean, we're left with this guy right here. So the error equals minus log of probability of observation given your model, which is basically your likelihood, minus the log of likelihood, basically, right? So you want to maximize the likelihood, and if you do that, the minus of that value will get minimized, hence your error gets minimized. So it means you're learning better and better sets of parameters. You're learning better and better, you're learning a better model. Remember that this whole formula over here, remember that previously we talked about that, and we said that error is nothing but minus the log of your posterior. So again, minus the log of your posterior, which is the probability of how much you believe in your model given the observation, equals minus log of your likelihood given m. So this is so these two are the same story, right? Very well. Before jumping into more details, okay, there's one more thing that we still haven't recapped here. So we said that we will introduce the idea of supervision learning into this whole thing, into this error function that we have come up with. And the way we did that was like this. So if you remember, we said that in a supervised learning where you're dealing with observation, like basically your input di and ti as your ground truth, right? And the model, your MLP, say your maximum likelihood, your multilayer perceptron network, gets a d as input and spits out y as your predictions. And you have the t, your target values, your ground truth, to compare your output with. And then depending on how much you've screwed up, basically, you will update the parameters in your MLP, and you learn better and better weights. Hence, basically, you will generate better and better outputs in the future. And that is the whole learning process. So, as you have noticed, the error has nothing to do, basically all the error is a minus the log of your likelihood, right? Probability of data data given your model, right? So let's focus a little bit more on this part, data given model. So model is basically, as we talked about, is nothing but the parameters you've got in your artificial neural networks. So I'm gonna replace m with w, or your weights, and I replaced d, your observation, with the input di and the target value ti, right? Di and ti, this is the pair, right? So the inputs and what the actual output corresponding to each one of those inputs are, right? And we said that using the rules of math, this equals to t of I given d of I and your w multiplied by the probability of actually seeing this particular input d of I given the weights, right? And then we said that the probability of di given w is equal to the probability of di, because the input of your model has nothing to do with the weights that you have in your model, with the parameters that you have, right? So again, the likelihood of d given w now equals to the probability of observing ground truth I given the input I and your current weights in your model multiplied by the probability of observing that input I, di, in the first place. Very well. Now, before going further down the line, I want to talk more about this likelihood, this probability of Ti given Di and W. I want to talk more about the idea of likelihood and what it actually means. And how is likelihood different from probability before we dig more and more into detail, because I don't want to lose you in the middle of the way. So let's feel more comfortable about that. But if you're already comfortable, you can just skip the next few slides and just jump into where we will do more derivations. Now, right, so let's start with a simple example. Let's say you have a continuous variable x, and let's say we are assuming that it is normally distributed, and the parameters of this normal distribution is mu, which is the mean, and the variance sigma squared, right? When we say that, it means that I can plot this normal distribution and say it looks like something like this, right? And the horizontal axis would be your x, and the vertical axis would be let's say the probability. Okay, when I say that the x is normally distributed with such a normal distribution, with such a Gaussian, it means that the center of your Gaussian is mu, and this guy right here, the variance, the sigma squared bit, it tells you how wide is your Gaussian, right? So the bigger it is, the wider your Gaussian is, and the smaller it gets, the tighter your Gaussian will get. And as it gets tighter, its height gets higher and higher, because if you remember, a distribution, a probability distribution, has to have an end, the area under the curve of 1, right? So basically, if I ask you that what is the probability, and please pay attention, this is very, very important. I mean, this used to give me such a pain, and I remember that I talked to some of the professors in my university, and I actually remember that day that they told me that you're getting too philosophical with this. Like, this is not important to focus on that much. But honestly, I think this is very important, because after I realized what it actually means, it helped me understand this whole concept of likelihood and error functions and everything that we're going to talk about later. So please pay attention. When I say that x is a continuous, remember, this is important, continuous random variable, it means that if I ask you what is the probability of x being, say, someone between, for instance, 3 and, say, 10. If I ask you a question like this, and this is basically your normal distribution, and say like mu is say mu equals 5, right? And then if I ask you what is the probability of, let me erase this bit, right? And if I ask you what is the probability of your x being in this, between this region, meaning 3 and say 10 is here, basically what you have to compute is you're gonna look at this part of this whole distribution and then calculate the area under the curve under this region, right? And that would be the probability of observing an x in this range, pay attention, in continuous random variables, it makes sense to say what is the probability of your random variable taking a value in a range, right? Pay attention. Still, I have not talked about likelihood whatsoever, right? So say it is like 1 over 3, whatever. It is a number between 0 and 1. Now, let's take a closer look. When I say that your random variable is distributed normally, it means that you can describe the probability of your random variable using a Gaussian distribution, right? So as a reminder, 2 pi standard deviation, the exponentiation of minus your random variable x minus the centroid, or basically the mean, squared divided by 2 times the variance. So this is the mathematical representation of a Gaussian distribution, a normal distribution. Right, and let's say, just for the case of simplicity, let's say that your standard deviation is 1, and let's just say that mu equals, I know I said 5 here, but I want to make this formula over here as simple as possible to illustrate a point. So let's just say your mu is 0, right? So the center of your Gaussian is somewhere around here. So it is something like this, right? Then this formula simplifies. But so again, you don't have to assume these numbers. I just want to make a point here. So that is why I'm considering these points, these particular values, to illustrate a point here. So this guy right here is 1, it gets eliminated, and this would be e to the power minus x minus 0 is x, so it would be x squared divided by 2, right? Because sigma squared is 1 squared, which is 1. Now I have a question, and this is a very important question. What does it mean if I have x as a continuous random variable? What does it mean if I ask you what is the probability of x equals a particular value, say 3? What does this mean? Can you compute that? Now, this is the funny part. If x is a continuous random variable, and if I ask about the probability of x being equal to a particular value, if you ask them from the experts, from the academicians, that was a minor mispronunciation problem. So they would tell you that it is equal to 0. What does it mean? It means that if x is continuous, and that is the important part, if x is continuous, it means that you can think of a rectangle, and just how many points do we have here? I mean, if I just draw this rectangular line which has a width and height, and like using a chalk or something, if I ask you how many points does this line include in it, you can say basically infinite number. I mean, it's too much. I mean, too many data points are, too many points are there. And if I ask you that, okay, you have this, I know it looks ugly, you have this dart, and I ask you to stand like 3 meters away from it and just throw it to that towards that line. And if I ask you, okay, what is the probability of this dart landing on this particular point right here. Not this point to the right, not another point to the left, this particular point over here. What is the probability of that happening? That is just ridiculously small, isn't it? It's because you got one point divided by the number of your data points, of your, say, points. And this guy right here is ridiculously large. You can think of as something that leans towards infinity. And this, my friends, is 0. Right? Because you've got infinite number of values right there. That is why when x is continuous, and if you ask for x getting a particular value, they always tell you that the probability is 0. Now, if x was not a continuous random variable, and say x was, say you have a dice, and the dice has 6 sides, right? The possible outcomes of x, say, is 1, 2, all the way to 6, right? So here your random variable x is a discrete random variable because it has just 6 outcomes. Now, if I tell you that, what is the probability of x being equal to a specific number, say 2? So how many 2's do we have in this set? Just 1. So one outcome has the value 2. And how many possible outcomes are there? 6. It would say the probability of x being equal to a particular value, say 2, is 1 over 6. Right? But the same story does not hold for a continuous random variable, which would give you the outcome of 0. Now, this is very important, actually. Why? And believe it or not, somewhere down the line it will link into the idea of likelihood, anti-error functions, and neural networks. Trust me, it will. But I want to make sure that we have a solid foundation before we jump into the next step. Now, I want to tell you that even though we're saying that the probability of x being equal to this exact value, this particular value, is 0 if x is continuous, even though we're claiming that, remember, if we assume, say, a distribution, whatever it is, it doesn't matter as long as it's a continuous distribution. Say, this is my distribution, this is the normal distribution that I have. Now, this is going to go crazy. So, the probability of, again, x equals, I'm going to consider the simplified case, e to the power minus x squared divided by 2. This is the simplified version. Now, if I tell you what is the probability of p of x equals, say, 0. Yeah, we say that if x is continuous, the probability of x equals 0 should be 0, right? But get this, if we plug in 0 here, we will get 1 over square root of 2 pi e to the powers 0 squared is 0, minus 0 is 0, divided by 2 is 0, so basically e to the power 0. And this guy right here will be 1, so we end up with a number. And pi is basically 3.14 something. Let's consider it to be 3, and then this would be 1 over square root of 6. Say this is 2 something, right? 2 point blah blah blah, whatever. It is roughly 0.5. Now, we said the probability of x equals 0 if x is continuous is 0, but yet if we actually plug in this value, we get 1 sorry, we get 0.5, and obviously these are not equal. Then what is this? What is this 0.5? So how can we interpret that? I mean, if we claim the probability of a continuous random variable being equal to a discrete value, an exact value, and not in a range, right? Then how can we interpret this number? My friends, this guy right here is called the likelihood. Oh, this is getting interesting. This is where we're gonna go back to the things that we were talking about, and believe me, this will all be connected eventually. Okay, so I'm gonna talk a little bit more about this idea of likelihood and probability, and then we will go back to our original discussion.